Look up at the night sky. On a clear night you might see a tiny, reddish point of light. That's Mars. For as long as we humans have been looking up, that little red dot has captured our imagination like nothing else. It's close enough to see, yet so far away. It feels familiar, polar ice caps, changing seasons, but it is also profoundly alien. This mix of familiar and strange makes Mars the ultimate destination in our collective dreams. Stories about Mars, books about Mars, blockbuster movies about Mars. All centered on one big question: could we go there? Could we live there? It's a question that drives us, pushes our science and engineering to the limit. Our curiosity is more than a passing fancy. We are explorers. Over the next hill, across the next ocean, on the next planet. Mars is the next step in our journey. Reachable with current technology, even if incredibly difficult. Every image sent back by curiosity and perseverance shows landscapes both beautiful and desolate. Vast canyons, towering volcanoes, ancient riverbeds hint at a very different past. Did life ever get a foothold there? Living on Mars isn't just sci-fi anymore. Brilliant minds are working on this. Engineers designing habitats, scientists figuring out food, astronauts training for deep space. But Mars is not a backup Earth. It is harsh and unforgiving. Hollywood loves a good disaster, and on the Red Planet, that often means a cataclysmic dust storm. In movies like The Martian, Mars is home to terrifying tempests powerful enough to shred vital equipment and even tip over massive rockets. We see the hero, Mark Watney, impaled by flying debris and left for dead by his crew, who are fleeing the storm's fury. It makes for a gripping story, but it's a dramatic portrayal that needs a little scientific correction. While Martian dust storms are real, and they can be absolutely massive, sometimes blanketing the entire planet, they just don't pack the same punch as a storm on Earth. The key difference is the incredibly thin Martian atmosphere, which is over 100 times less dense than our own. A storm's destructive force comes from both wind speed and the density of the air pushing against you. Even though Martian winds can reach speeds of 60 miles per hour, the air is so thin that the pressure they exert is minimal. To put it in perspective, standing in that 60-mile-per-hour Martian gale would feel like a gentle 11-mile-per-hour breeze on Earth. Annoying perhaps, but you wouldn't be knocked over and a rocket certainly wouldn't be tipped. So if they aren't physically destructive, what's the big deal? The problem isn't the punch, it's the persistence and pervasiveness of the dust itself. These storms can loft fine dust high into the atmosphere for weeks or even months, blocking out the sun. For solar-powered missions, this is a death sentence. In 2018, a planet-encircling storm plunged Mars into darkness, leading to the demise of the legendary Opportunity rover. Unable to recharge, it fell silent forever. This is precisely why newer rovers like Curiosity and Perseverance are nuclear-powered, making them immune to this particular threat. But the dust is also an engineering nightmare. The particles are microscopic, with sharp, jagged edges, more like tiny shards of volcanic glass than smooth sand. This makes them highly abrasive, and they're electrostatically charged, meaning they cling to everything like stubborn styrofoam. This isn't just an annoyance, it's a critical failure risk. It can coat camera lenses, jam sensitive gears, and even create pathways for electrical short circuits. For future human explorers, the threat is even more personal. If this fine dust, smaller than particles in cigarette smoke, gets inside a habitat, it becomes a major respiratory hazard. Worse, the Martian soil is laced with perchlorates, a class of toxic salts. Long-term exposure through inhalation or ingestion could lead to thyroid problems and other serious health issues. Future missions will require advanced dust mitigation strategies, like decontamination zones in airlocks where astronauts are zapped with an opposing electrical charge to shed the clinging particles before entering the clean habitat. So while a Martian dust storm won't dramatically blow an astronaut off their feet, its true danger is far more insidious. It's a slow, grinding threat that can starve a rover of power, wear down critical machinery, and pose a long-term health risk to anyone brave enough to call Mars home. The reality of Mars is often less cinematic, but far more complex and challenging than fiction. The search for water on Mars is one of the most exciting and often frustrating fields in planetary science. For decades we've been chasing ghosts and glimmers of it across the red planet. And for good reason. Water is the key ingredient for life as we know it, the one non-negotiable element in our search for biology beyond Earth. And in 2018 it seemed like we'd hit the jackpot. Headlines around the world buzzed with the news. A potential huge liquid water lake detected beneath the South Polar ice cap. The idea of a vast hidden Martian ocean, a potential habitat for life, captured the public's imagination like few discoveries before it. The tantalizing clue came from the European Space Agency's Mars Express orbiter. Its MARSIS instrument, short for Mars Advanced Radar for Subsurface and Ionosphere Sounding, sends low-frequency radio waves through the ice. These waves bounce back differently depending on what they hit. And in 2018, scientists found an area where the signal was unusually bright, a strong reflection consistent with a large body of liquid water. The data pointed to a feature roughly 12 miles across, buried a mile beneath the solid ice. It was a thrilling prospect, but the scientific community remained cautiously optimistic because a huge question loomed. The temperature at that depth is estimated to be a frigid -90 degrees Fahrenheit. For water to remain liquid, it would need to be an extremely concentrated brine, far saltier than Earth's oceans. Could such a large body of water really exist in those conditions? As other teams began to scrutinize the data, new theories emerged. A team at NASA's Jet Propulsion Laboratory, including Aditya Kular and Jeffrey Plout, expanded the search. They found not one, but dozens of similar bright reflections scattered around the South Pole, some in areas thought to be too cold even for salty brines. Their 2021 work proposed an alternative. These signals might not be water at all. Instead, they could be caused by specific types of iron-rich clays or metallic minerals, which can also produce bright radar reflections. This doesn't completely rule out the possibility of small, isolated pockets of brine, but it significantly weakens the evidence for a single vast subglacial lake. This is the scientific process in action. An exciting hypothesis is proposed, it inspires more research, and with more data, our understanding evolves. It's a roller coaster of discovery, and the story of water on Mars is full of these twists. For decades, we've known Mars wasn't always the frozen desert it is today. The evidence is carved into its surface. Massive dried-up river valleys, sprawling deltas, and hydrated minerals found by rovers are undeniable proof of a warmer, wetter past. NASA's Perseverance rover is currently exploring one such location, Jezero Crater, the floor of what was once a deep, tranquil lake, fed by a flowing river. Even more recently, another water story took a turn. Features called recurring slope lineae, dark streaks that appear on crater walls in the summer, look tantalizingly like seeping brines. But higher-resolution images from the HiRISE camera revealed they behave like dry sand, not wet soil. The current thinking is that these are tiny avalanches of dust and sand, with seasonal changes in surface hydration causing the darkening, not flowing liquid. So while the prospects for large liquid lakes and flowing surface trickles have dimmed, the bigger picture is incredibly bright. Vast quantities of water ice are confirmed to exist, not just in the polar caps but also buried just beneath the surface at surprisingly low latitudes. This is a game-changer for human exploration. Future astronauts won't need to bring all their water from Earth. They could land, dig down a few feet, and access a nearly limitless supply of ice. This ice can be melted for drinking water, used to grow crops, and split into oxygen for breathing and hydrogen for rocket fuel. The water is there, a frozen reservoir waiting to unlock the future of humanity on Mars. Of all the dangers on Mars, perhaps the most serious is one you can't see, hear, or feel: radiation. Here on Earth we are incredibly lucky. We live inside a protective bubble created by our magnetic field and thick atmosphere that shields us from two main threats: a constant stream of galactic cosmic rays from deep space, and sudden solar particle events from our own sun. On Mars, it's a different story. The planet lost its global magnetic field billions of years ago, and its atmosphere is now 100 times thinner than Earth's, offering almost no protection. The surface is constantly blasted with high levels of radiation. Curiosity's RAD instrument shows even the journey delivers a significant dose, and on the surface, exposure keeps adding up, easily exceeding an astronaut's entire career limit on long missions. Radiation can damage DNA, increasing cancer risk, harm the central nervous system, impair performance, cause cataracts, and affect the heart. A powerful solar particle event could deliver a dangerous dose in hours if unprotected. Solutions require putting mass between astronauts and the sky, heavily shielded habitats, using meters of regolith as a barrier, or building underground in natural lava tubes and caves. But spacesuits also need advanced shielding, adding weight and reducing flexibility. There is just no easy fix. The challenge is immense, which is why science fiction often inspires real science, especially with Mars. Take The Martian. Could you really grow potatoes in regolith? The soil has minerals, but it's also laced with toxic perchlorate salts, You'd need to thoroughly wash the soil first to remove these toxins, a critical step not shown in the movie. And making water by burning hydrazine? While chemically plausible, it's incredibly risky. In reality, astronauts will likely mine the abundant water ice found just beneath the surface, a discovery confirmed by the Phoenix lander, and process it. 1,000-kilometer drives and easy repairs make great cinema, but real operations in bulky, pressurized suits will be slow, methodical, and dangerous in the extreme cold. The Mars Yard shows how teams solve problems Watney faced, slowly, methodically, and together as a team. Despite everything we've learned, Mars still holds many secrets. Perseverance is caching samples for the ambitious Mars Sample Return, a joint NASA-ESA mission. The complex plan involves a future lander and a small rocket, a Mars ascent vehicle, to launch those samples into orbit. There, another spacecraft will capture them for the journey back to Earth, allowing us to search for signs of past life in our most advanced labs. Missions like MAVEN continue to study how Mars lost its atmosphere and magnetic field, confirming it was stripped away by the solar wind. Looking ahead, living off the land, or ISRU, is key. The MOXIE experiment on Perseverance proved we can make oxygen from CO2 via electrolysis. Future systems will use Martian water and air to produce not just oxygen and water, but also methane for rocket fuel to power the trip home. Every data point on radiation, dust, geology, and weather builds the blueprint for humanity's next giant leap.